Hello, everyone. Uh, Thanks for coming for the last lecture of this course on offering strategy in ancillary service markets with a focus on Nordic ancillary service markets. Uh, yes, this is the last lecture, lecture number 10. First, we are going to have a recap of Nordic ancillary service market based on what you learned in lecture number 6. It will be a quick recap, and then based on that, we will build scientific foundation how we can bid. So again, today we take a perspective from a flexibility service provider. It could be a flexibility aggregator. It could be, I don't know, a big flexible asset, maybe a thermal energy or whatever. But we will have some real cases, real examples today. And the idea is that, okay, how can I participate in Nordic ancillary service markets with the goal of maximizing profit? Is it clear? Good. So, recap. Let's start with a recap. You saw this picture before in lecture number 6, right? It shows the map of different frequency areas in Europe. Of course, everywhere frequency, the nominal frequency is 50 hertz, but it doesn't mean that everywhere in Europe the frequency is synchronous. It's not. So the big part is blue. It's continental Europe. And you see that the part of Denmark, DK1, is part of continental Europe. Then the green one is Nordic synchronous area. And part of Denmark, DK1, is part of Nordic area. And then we have areas for UK and Ireland. Have you noticed in news that something has changed in this picture in the recent months? Yes? Baltics. So what happened to Baltic synchronous area? Yes. Now the purple area it's also blue. So you can replace the purple countries, the Baltic countries, with blue. Now also the Baltic countries are part of continental Europe. It happened a month ago or something like that. 9th of February. Okay, more than a month ago. Thanks. How do you know that exactly, the date? You follow. Yes, so as I said, DK1 and DK2. So Denmark is the only country that it's part of two frequency areas. And that's why Energinet, it puts Energinet in an interesting position that they have to be aware of all the ancillary services in two different areas. Then remember these pictures from lecture number 6 that the upper plot shows the three main services, ancillary services in DK1 and in continental Europe. So we talked about FCR, Frequency Containment Reserve, AFRR as the second fastest service, Automatic Frequency Restoration Reserve, and then MFRR, Manual Frequency Restoration Reserve. So in the upper plot, you can see that what's the range of activation and the ramp up for every service. So whenever something happens, first FCR is automatic service. It's a very fast service, and it's being activated automatically, so just by measuring frequency. Then AFRR, which is also automatic service, and then MFRR, which is the manual service. It should be being activated by system operator. While the lower plot shows ancillary services in Nordic area, it's a smaller system, also with high penetration of renewables, including hydro, wind, solar, and that's why you can call it low inertia system. That's why we need more services to keep the system stable. In terms of, you need more balancing services. That's why we have more services, starting with FFR, Fast Frequency Reserve. It's the fastest service. And then we have, now in Nordic, FCR is split to two services, FCRD and FCRN. D stands for disturbance, N stands for normal. So if you remember FCRD, we have two FCRD up and down. FCRD down is being activated when frequency is about 50.1. I hope I remember correctly. And FCRD up is being activated if frequency is going below 49.9. And if frequency is a normal situation, it's between 49.9 and 50.1 hertz. We can say that the system is in a normal situation and it's only FCRN is being activated. Also, we have AFRR and MFRR. And why we are interested in these services in this course? Because for every single service here, we have a market. So TSO in Denmark, Energinet, runs a market, a capacity market, a day before, in a day ahead advance, before day ahead market clearing, to buy capacity. Yeah, you remember that, right? Energinet buys capacity. There are capacity prices in DKK or euro per megawatt. Not megawatt hour, per megawatt. And again, these are slides recap from lecture number 6. So this slide from Energinet shows that the technicalities of different services. So in left DK1, FCR, AFRR, MFRR, and in right DK2 services. So in terms of ramp up, activation time, blah, blah. There might be a case that this data are, all the times these technicalities are being updated. So I'm not sure that I can't say that 100% all these numbers are updated. So all the times you need to check an Energinet website and get the most updated numbers. This is also a slide from Energinet, shows that what technologies can participate in different markets depending how fast they are in responding to a signal. So for example, in the case of DK2, you see that ventilation or batteries, they can participate in FFR. And since they are fast enough to participate in FFR, they can participate in all other services as well. In the case of FCRD and N, you see that, for example, electrolyzer is there, or electric vehicles are there. So they can participate in FCR markets, but not in FFR. Is it clear? And again, always you have to get the most updated guideline from Energinet or other TSOs to see that what the current grid code and guidelines are. And also, if you remember this slide from lecture number 6, you will see that for the case of FCRD up and down in DK2, the activation is very rare, while FCRN is all the times being activated either for up or down, right? Because most of the times, the system, the frequencies, the frequency of the system is between 49 and 50.1, while it happens very rarely that the frequency goes beyond 50.1 or go below 49.9. Yeah, so as I said, it's very rare to see that FCRD is being activated. But actually it happened recently several times. Every time, for example, by a trip in nuclear power plants in Finland or Sweden, it happened a few times recently, and all the times FCRD services were activated. So this is another slide. So it shows the prices, historical prices for different services, euro per megawatt, not megawatt hour. And as you see, the orange one is FCRD down, which has been introduced early 2022. I think the lecture 6, I also showed you an updated price picture for FCRD, though it used to, FCRD market used to have very high prices. It's not the case anymore today, right? So that's why FCRD market is a bit less popular than before for bidding. So in the case of FCRD, how it works in Denmark in DK2 is that D-1, Energinet buys services. For example, in the case of Energinet, FCRD up and down, 41 megawatt of FCRD up and 38 megawatt of FCRD down. That's what Energinet is buying every day for every hour. Again, these numbers might be updated, but this is at least the information based on the time Marco, my student, Yeah, you remember Marco, right? He gave a lecture, invited lecture a few weeks ago. Yeah, he contacted every TSO by phone asking, okay, how much services you buy every hour. So at least these are the numbers based on the time that Marco contacted TSOs. Remember, Statnet Norwegian TSO, Fingrid Finnish TSO, Svenska Kraftnät Swedish TSO, and Energinet is Danish TSO. And then in the real time, if it's needed, services will be activated, and then we will check TSOs, they calculate ex post financial settlements. And if there is a failure in activation, then the service provider will be penalized. Good. It was a bit fast recap, right? So there was nothing new there. But do you have any questions so far? Did you follow everything perfectly? Yes?
Can you maybe elaborate on the Spanish outage based on what we learned?
Yeah, well, these days, yeah, you heard that there was a big blackout in Spain and then in Portugal, right? It was last week or 2 weeks? Yeah, last week. I'm not sure. There are many people interviewing, talking about reasons, but all are hypotheses. I'm not sure that the real reason is out there. So I don't think, I think we have to wait and see what was the main reason. So I'm also very interested to know what the reason was. But I think at the moment we don't have enough information to know, at least as far as I know. So we have to wait for Spanish TSO, Red Electrica, to see that what happened, what caused this blackout. But we know that before blackout, high frequency fluctuations happened observed, right? But what reason is behind this blackout, I think is still unknown. Good. So today, I like to take the perspective of a stochastic flexible assets. And let's say that how stochastic flexible assets can bid their flexibility to ancillary service markets. What do we mean by stochastic flexible assets? Can you give me an example? Assets that they are flexible, but also stochastic. An example? For example, yeah, please. EVs, electric vehicles. They are just distributed batteries, right? Distributed across the network. They are fast, they are flexible, but they are stochastic. You don't know in advance well how much flexibility they can provide. It depends if they are grid connected. It depends what is the battery charging status that time if they are connected to grid, right? So it is a stochastic. You can't 100% on them, or you don't have 100% perfect information how much flexibility they can provide tomorrow, because you are buying flexibility the day before, right? Can you give me another example? Flexible asset, fast responding asset, but stochastic. Heat pumps, right? You don't know exactly how much flexibility heat pumps they can provide, flexibility they can provide the day after, the day before. Or even wind turbines. I mean, by changing the pitch, they can provide flexibility to some extent, right? But again, it depends how much production they're going to have. So it's also stochastic. And here, I mean, we cannot, there is a minimum bit size for participating in ancillary service markets, right? So it's not possible for every small asset to participate directly in the market. So that's why we think about aggregators, right? Aggregators. So aggregators, they pool a large number of stochastic assets, and then they participate in flexibility markets or in ancillary service markets. For example, IBM in Copenhagen, they used to build a platform called Flex Platform, just by connecting many different assets and then participating in different markets. But I recently heard that it has been sold to Andil. So you see the main reason of aggregator, right? To pool a large number of flexible assets and then harnessing or collecting all flexibility from the portfolio and then participating in different ancillary service markets. Also, aggregators, they can participate in local flexibility markets, for example, for DSOs, to provide congestion management services for DSOs, but it's a different story. I'm not covering that in this course. Okay? Is it clear? Also, do you think by collecting more assets in a portfolio, assuming that hopefully there is a negative correlation among them, maybe, do you think that then it helps us to have more predictable portfolio or not? There is something called aggregation effect, right? So more uncertainties, more stochastic assets you pool, it gets easier or more straightforward to predict their flexibility, right? And especially if you manage to collect devices with negative correlation. For example, when one has more flexibility, the other one has less flexibility and other way around, then it will help you to have a good level of flexibility all the times. So how to optimally aggregate assets to build an aggregation, a portfolio of stochastic assets itself is a big topic. But here what I'm talking is how an aggregator with a certain portfolio can participate in Nordic ancillary service markets. Is it clear? Very good. So here I can only talk about participating in FCRD markets, up and down, but the same concept you can consider it for any other ancillary service markets like AFRR or MFRR. Maybe for MFRR it will be a bit harder, more complex than what I'm going to present, because MFRR is energy intensive service, while FCRD is not. So when it's being activated, the energy it's being charged or discharged is kind of negligible, because the duration is very short, the duration of activation. Good. So the work I present is based on the master thesis of two gentlemen, Emil and Gustav, under supervision of my former PhD student, Peter Gale, and myself. So the first things Gustav and Emil did, they contacted Spiri. It's a EV smart charging developers. They don't have any asset. They provide service, software solutions. And they got information for, I think, 1,400 EVs, the consumption data, the historical data, from March 24, 2022 to March 21, 2023. So we got that data. And the data we got was at minute level. It was not in minute level, but it was not perfect data, but Gustav and Emil, they worked on that, and they made it minute level consumption data. So is it clear? We have historical data, minute level, for power consumption of 1,400 EVs in all over Denmark. So, for example, for the example hour, it's an example hour, you can see the power consumption. The power consumption, the total power consumption of 1,400 EVs looks like this. So we call it consumption baseline. The red curve shows the maximum consumption our EVs could have in that minute. And you see that it's time changing, it's time variant. Do you know why it's time variant? Because the number of the grid connected EVs is changing, right? EVs are connected or disconnected from the grid all over the time. So that's why The red curve, which is the maximum consumption, is time invariant. And the realization of consumption is like this. So assuming that you can charge or discharge all these connected EVs fully, so you can stop their consumption to zero, or you can, in a very rapidly, you can increase their consumption to the maximum consumption. By assuming that, it means that they are fully 100% flexible. We can say that the area under this black curve is upward reserve, because by consuming less, they are providing upregulation, like a demand, right? You can see it as a big demand. While by increasing the consumption, they provide downregulation, downward flexibility. Is it clear? But this is all from the historical data. So the purple area is potential for downregulation, while the blue area, light blue area, is a potential for upregulation. And here, the upregulation is only based on reducing consumption. It's not based on V2G. What is V2G? Vehicle to grid. The batteries are injecting to the system. We don't model it in this work. It just, so we provide FCRD upward regulation, only by reducing the consumption. So if you think of a big industrial plant, it's the same. By reducing the consumption, for a moment, you provide upward regulation. Clear? Good. But this is for only 1 hour, one historical hour. You cannot just, there is uncertainty. In different hours, historical hours, different realization of potential for FCRD up and down happened. So what Emil and Gustav did, they built these two CDFs, cumulative distribution functions. So now, again, it's a minute level. So you see that for every minute over a day, what is the distribution of flexibility up and flexibility, downward flexibility? Upward flexibility means reduction of consumption. Downward flexibility means increasing consumption. So what does it mean? For example, this moment, this dot says that probability is 0 to have a potential for at least 2,000 kilowatt FCRD up in our 6 a.m. So remember, we got data for a year. So we can derive this CDF function, right? It's just data analysis. Or for example, saying that the probability is 1, it's a dark area. Probability is 1 to have a potential for at least 200 kilowatt FCRD up in our 3 a.m. Right? That's what we got from all historical data. Is it clear? So why we are using historical data? Here we use historical data as a proxy, as a way or representative of what is going to happen in future. So historical data is representative of future flexibility. So we use the historical data directly for bidding problem of our flexibility that will happen tomorrow. The different way that you can see is that, no, I take the historical flexibility, I forecast flexibility, and then I use my forecast for bidding problem. That's a different approach that you can take. Is it clear? Good. But here we are making a big assumption, right? We assume that historical data is representative of future. But if it's not the case, then everything we are doing is wrong. Good. Yeah, I think I discussed about this non-stationarity. For example, if the data, historical data, is not representative of future, then what we are doing is misleading. Good. So far you learned how from historical data we can get CDF functions of how much flexibility we have. Good. Now let's take Energinet's perspective. I told you several times in this course that I'm very happy that Energinet is a leading TSO with having new initiatives, helping stochastic assets to provide flexibility services to the system. One of the reasons is P90 requirement. I think we discussed about P requirement in lecture 6, but we will revisit that. But if you want to read more about P90 requirement in Energinet report, you can click to this report by Energinet. You'll see the link here. It's a report published in 2024, but I think Energinet recently also revised that. So also you can find the revised versions. Good. This is the text I copied from an Energinet report, and I highlighted one sentence by red. Could you please read the text for a minute? So it's a requirement for flexibility service providers, those who participate or those who submit bids to any ancillary service market in Denmark. It says that the participants, this means that participants' prognosis, the forecast of participants in the market, which must be approved by Energinet. So this means that before you participate in ancillary service markets, you should be pre-qualified by Energinet. So first, Energinet should stamp that, yes, you are eligible to participate in ancillary service markets. For that, you need to go for a pre-qualification process. And in the pre-qualification process, you should show Energinet that you have a good forecast. Anyway, so must be approved by Energinet. Evaluates that the probability is 10% that the sold capacity is not available. So for example, you submit a bid of X kilowatt or X megawatt to one of the ancillary service markets. You will be kept eligible to participate in that market if we realize that the probability, the chance that that bid is fully available tomorrow is at least 90%. So it means that there is only the chance of maximum 10% that what you submitted is not available. Is it clear? This entails that there is a 90% chance that the sold capacity or more is available. One also interesting thing is the last sentence. The available part will, with a high probability, be close to the sold capacity. It says that, okay, 10% of the times you may fail, but it's still about the magnitude of failure. You are expected to have a small failure. That's the last sentence about the magnitude. Okay, how do you interpret this requirement? So how I see it is as following, but tell me. Let's say that you have a consumption. So let's say that you have a perfect forecast of how much your EV fleet will consume tomorrow in a specific hour. Let's say from 2 p.m. to 3 p.m. Let's say that you know exactly that this will be your consumption, right? But we know that it's uncertain. Okay, if it was not P90, it was P100. Remember, also the bids you submit, the ancillary service market, I mean, it's hourly. Soon it will be 15 minutes. Already some of them is 15 minutes. But for now, let's say that we submit a bid for each hour of the next day. So for example, for 2 p.m. to 3 p.m. Okay, and imagine that you exactly know your future consumption. a realistic case, right? If it was P100, it means that whatever you submit as a bid, let's say for FCRD up, it should be 100% available. Then what would be your bid? This area is potential for up-regulation, right? Imagine that you can make your consumption zero. You have full flexibility. So if we had P100, not P90, P100, all the times your bid should be available, all the times over the hour. What would be your hour, your bid? Will it be here, will it be here, will it be here, will it be here? What would be your optimal bid in terms of kilowatt? Are you following me? So, answer.
Always at the maximum.
Maximum. So, your bid here? That level?
So just following the...
You should have one bid, one number for the whole hour. You cannot say that my bid is changing over time. The minimum. So you go for minimum, which is here. I don't know, for example, it's 10 kilowatt. So you go for 10 kilowatt, right? Do you also agree that you go for 10 kilowatt? You also agree. What?
Then you have 100% chance to always do
Yes. So now you have 100% chance that whenever, if the service is being activated, you have full availability of the service and you can successfully deliver the service by reducing the consumption. Are you following me? Good. I'm trying to find a different color. Okay, now we have P90. So Energinet said not P100, now P90 is also fine by me. Okay, now by this new grid code, this new requirement by Energinet, what would be your bid? Yes? A bit higher or a bit lower?
A bit lower, 10%.
10% lower, so your bid will be 9 kilowatt? Higher, 11? Okay, let's say 11 or 9. Who says 9? Who says 11? Okay, majority says 11. So one of those who says 11. So if I bid here, okay, it might be more than 10% what I not draw, but you see what I'm saying. So why 11?
I mean, the area that's above the your P100 should
Yeah.
be 10%.
Yeah. So it means that now if I'm activated at this point of time, I can only deliver flexibility up to this amount. And this is my failure, my overbidding. True? So if I'm activated by 11 kilowatt, at this point of time, I can reduce my consumptions only 10 kilowatt, for example. And 1 kilowatt is overbidding. I have shortfall because my consumption is 10 kilowatt. How can I provide flexibility up of 11 kilowatt? I can't. Is it clear? Here we are talking only about the chance, not magnitude of overbidding. So when overbidding is happening in this case, so overbidding is happening in all these areas, right? If I'm activated at that time period, I have overbidding, I have reserve shortfall. I cannot fully deliver what I promised. And it looks that it's more than 10%. So this looks like P50 or P40. Is it clear? So P90 might be a case something like here. 10% of the times you can't deliver fully what you promised. Did you follow me? Was it clear? But remember, this is the idealistic case because I assume that this baseline is fully available a day before. When do you submit the bid? A day before. So your future consumption, at least in the case of EVs or heat pumps, the aggregation of EVs, it's not deterministic, it's not perfect. So what you have is a distribution. maybe even a more band for that, right? So then, if you have uncertain consumption for tomorrow for every hour, now with this stochastic baseline, consumption baseline, you have to decide what bit you want to submit following P90. Did you follow me? Good. So when I say reserve, shortfall, or overbidding, I'm talking about, for example, this case that I bid this, and now this part is not available. So for an available part of reserve, we refer it to as overbidding. It means that you bid more, or reserve shortfall. They are the same things. Clear? Good. So, yes, we said that there is pre-qualification. Imagine that you got accepted, you are eligible to participate in FCRD market. Good. Now you submit a bid for tomorrow specific hour, 2 p.m. to 3 p.m., and you say my bid is, I don't know, 1 megawatt in FCRD. And you say that, yeah, I follow P90 requirement. Remember, we discussed that in the case of FCRD, the activation is not often. Maybe the service is being activated, I don't know, a few times per year. So how Energinet can know that you are fulfilling P90? Is the question clear? One way is saying that, okay, maybe over a year I will activate 10 times. You know, FCRD is not being activated often. And if your failure when I activate is more than 10%, then you are not following the P90. But it doesn't look a good strategy, right? Because activation is not happening all the times. And to be honest, we should not link checking the quality of the bids to activations. We should have a strategy independent of activation, saying that, okay, we are not just relying on activations. We want to know whether the bid you submitted really follows P90 requirement or not. How can we do that? Let's say that you submitted 1 megawatt FCRD up bid for tomorrow, 2 to 3 p.m. You submitted that. And luckily, the system let's say that we wait for tomorrow, and then we realize that the system was in a good condition. We never activated the service. But how can we know that this 1 megawatt was really available? How can we know that? Put yourself in Energinet's position. Any idea? I'm sure you have some good ideas. So you submitted 1 megawatt. Good. Now, after tomorrow, the day after, what else you can ask from the service provider to see that whether that 1 megawatt was available or not? The real consumption, right? You could see the real consumption. So what I'm saying is that D minus 1, you submit this. Then this is the real time. The day after, D plus 1, X post, this is X under, this is X post. X post, you can ask the service provider, give me your real consumption. For example, then you will see that it's like this. That's the realized consumption. then you can see that, okay, whether 1 megawatt was available or not. So you can check it ex post. And Energinet can check it ex post. Is it clear? But does this mean that Energinet should check ex post every single service provider for every hour whether P90 is met? It's a big work, right? Then Energinet should hire 500 employees just to check that. So Thomas Dalgas is my good contact at Energinet. So when I posted something about P90, a good colleague, Harry, from that time from TNO, I think he recently changed his place. He asked that, okay, interesting, how is the requirement enforced? Since only the realizations are visible and the underlying distribution is usually not. How do bidders prove a 90% probability? And what Thomas from Energinet replied, it's based on at least 3 months of historical performance. So you don't check, Energinet doesn't check every hour next day. No, checks the last 3 months, saying that, okay, the last 3 months, so what Energinet checks saying that, okay, this is now. For the last 3 months, what was your bid? For example, your bid was something like this, 1 bid per hour. And also they check your realized consumptions and check at what percent of the times you had overbidding. If it's more than 10%, then you have problem. Is it clear? So let's read what Thomas replied. This is LinkedIn things. It's just a screenshot from LinkedIn. Based on at least 3 months of historical performance where the P90 proved to be available at least 15% of the times. Why 15? And Energinet, because it's a new requirement, and Energinet said, okay, 10%, but also I give you 5% buffer until you get used to this requirement. But this 15 will become 10% soon. Or maybe it's already 50%. So it's a binary consideration. We continuously monitor the performance of both the physical delivery and forecast as well, which allow for a low entry criteria. Okay, so it's based on the historical performance in the last 3 months. Yes, please.
Does that mean that you have to wait?
Sorry, I can't hear.
Does that mean that you have to wait 3 months before you can be considered for ancillary services?
No, so, good question. Then Energinet has 2 evaluations. One is pre-qualification. You want to participate in that market, there is a pre-qualification process that you should fulfill with Energinet before being able to participate in ancillary service market. Now you are pre-qualified. Now you start bidding. Now this is not pre-qualification, this is ex-post assessment, the second evaluation. It's being done every 3 months, for example. I don't know if Energinet keeps this 3 months or not. And whenever they realize that now your violation is more than 15% or 10%, then you will lose your pre-qualification. It's like you're losing your driving license. You should go and test again. You should go and apply for pre-qualification again. Is it clear? And by the way, if you are activated, and you are unsuccessful in delivery, then TSO needs to find alternative resource for activation. Also, you will be penalized for unsuccessful activation and being paid for the alternative resource. But in the case of FCRD, since it's not very common to activate that service, you can assume that will not happen a lot. Are you all following me? Good. Okay, before talking about mathematics, let me ask a question and then we can have a break. As far as I know, it's only Energinet that has this P90. Every other TSOs, they have P100. For example, in Netherlands, if I'm not wrong, Tenet, they have a market called a secondary auction for AFRR, for example, saying that, if you already sold, if you already, if as an aggregator, you have a bit of 1 megawatt in participating in AFRR, and now after market cleared, you realize that that 1 megawatt is not available anymore. They define a secondary market that you can go and sell your 1 megawatt to someone else. For example, saying that, I have 1 megawatt AFRR, but I can't produce that. How can I do? Is there anyone who can take my 1 megawatt and pay me something? Is it clear what I'm saying? So, but still, Tenet or others, they keep P100. It means that if you participate in the market, you should be 100% sure that your service is available all the times. And Energinet made the life harder for itself by saying P90, right? It means that you formally accept that 10% of the times the service can be failed. Why Energinet is doing that? You are answering your asked question.
Maybe answer.
Go ahead, please.
Lower entry barriers for
Pardon me?
lower entry barriers for new participants.
Yeah, exactly. I think the answer is this. Yes, lower entry barriers for, yes. For example, think of EV aggregators or wind aggregators or heat pump aggregators. If you ask them 100% reliability, it means that you close the door for them. If you want them to be part of the solution, if you want them, balancing is one of the challenges against green transition, right? With more wind, more solar, you have more imbalances. So who should help the system with imbalances? It should be renewables itself, or EV, or demand-side stochastic assets themselves. But if you ask them to provide P100 reliability, then you are not opening the door for them, right? Okay, good. So you are lowering entry barriers for them. But on the other hand, now TSO and Energinet will have more probability to have failed services. Then what's your solution for that? Yeah? Maybe Energinet can buy more of ancillary services.
Sure, since you're letting more participants, you also have, you're using this pooling effect again. So maybe some participants will compensate for the losses of the others.
Very good. First of all, we may see, that's a PhD topic, and I love to do that. Do we need, as a TSO perspective, do we need to buy more services because of P90? If so, how much more? First. Second, do you have a question? Okay. The second question is that by buying more, it means that TSO pays more or not. By P90, do we have more cost for TSO? Let's say that, yes, TSO should buy more ancillary services. But at what price? Now we have more suppliers than before, right? By P90, there are more suppliers. More suppliers means lower price, right? If you have scarcity, the price is higher. Now with P90, there is more flexibility to offer to the system. That's why the price may go down. On the other hand, because of P90, you may need to buy more to compensate 10% of the times if we say that the aggregation effect will not help us, right? So what I'm saying is that with P90 looks clever, because though you may need to buy more services, but on the other hand, the service cost may be lowering. Are you following me? But to see exactly what the case is in Denmark and other countries, I think we need more data, more analysis to really understand what implications of P90 are. Yes?
Why P90 and not P80?
That's really good questions. We now start with the industrial PhD with Energinet. Hopefully it will be funded. The first question is, what is optimal level? Energinet started with P90. Why? I don't know. You should ask Thomas. But maybe and I think it's case sensitive. Maybe for Denmark, we may realize P91 is the best, or P89. So making P90 is a good step. Is it optimal? Who knows? Did I answer? One question, final question, and then we can go for a break. I forgot that. In finding the optimal level, P90 or P85 or P95, what it matters? As a TSO, what should you be very worried? What is your extreme bad case? What is the extreme worst things that can happen to you? Yes?
If all of them are at 90 at the same time.
Exactly. All of them fail at the same time. And you cannot blame them. They say that, okay, all of us, we are fulfilling 90% of the times. But unluckily, all 10% happens at the same time. Then you have a big problem, like a Spanish blackout. So as a TSO, what you should analyze, the correlation of failures. For example, if you buy all your services from wind turbines, then you have a problem, I can tell you. Because when the wind is not blowing, all the wind turbines will fail. But if you optimally buy, if you have some resource allocation, and you don't put all your eggs in the same basket, maybe you can say that, okay, when the wind is failing, maybe my EVs will help, maybe my heat pumps will help. So that's a big question, how we can optimize our portfolio. So if we have a very good negative correlation, not positive, then we are good. Then maybe we can go P85. But if we say that, no, all our services are coming from wind, oh, P90 is not a good idea, go for P100. So what is the optimal level of this P90 or 80 or whatever? I think it depends on what resources you have and how correlated they may fail at the same time. Is it clear? So that's why I don't think we can say P90 for all countries. No. We have to say what the case is. But going, or how to say, this is a good initiative though, not saying P100 all the times. We have to open the door for renewables to help with balancing. Hope you agree. So we discussed about P90 requirement and what it means and how Energinet evaluates that ex post, and yeah, why it might be a good idea. But now let's talk about mathematical representation of the P90 requirement from a stakeholder perspective. So let's say that, remember our EV example, we have 1,400 EV in our fleet, and we want to optimally bid in FCRD up and FCRD down markets. Let's start with this. Let's only start with only FCRD up for now. So we want to C up is our bid in kilowatt or in megawatt of FCRD up in a given hour. So since this problem is solved per hour, I didn't put extra index of H, for example, but if you want, you can do that. So this is a bid, FCRD up bid in kilowatt in a given hour or in a given 15 minutes, depending on time resolution or the market time unit, MTU. And we know that the bid should be non-negative, greater than or equal to 0. Good. So you can say that I'm trying to maximize my profit or maximize my capacity. Here, the optimization will be the same. So either you try to maximize in kilowatt, but since there's here in this list, in this case, there is no time linking constraint, then maximizing capacity is identical than saying maximizing the price of FCRD up times C up. These two are the same, right? It just adds a weight for now. So simply I'm saying that, okay, I'm maximizing the quantity. And then subject to a weird constraint. That constraint, we call it chance constraint. So C up still is our variable, FCRD up. M is indexed for minutes. Why minutes? Because we have data in minute resolution. If you have different resolution, use different resolution. If you have second level resolution, use per second. FM up is available flexibility up in minute M. So it comes from this CDFs. So this is the flexibility up. So in every minute, you have a distribution of available flexibility. Is it a given fixed number? No. There is a distribution of available flexibility up for every minute. How did we build that distribution? Based on historical data. Is it clear? So this value, Fm, available flexibility, available upward flexibility for minute M, comes from that figure. It's not a single value. It's an uncertain parameter. There is a distribution, empirical distribution, for that value. Are you following me? So we discussed that. Forget about that. So we always want to make sure that we bid up to how much flexibility we have. But how much flexibility we have is stochastic. So this is a stochastic parameter. This is our variable. We have that constraint per minute. And now we have this function of P with a constraint greater than or equal to 1 minus epsilon. And in our case, because of P90, epsilon is 0.1. So this is 0.9. This is a chance constraint. Do you know what it means? What does this constraint imply? Do you have any idea? Have you seen it before? It says that the probability of this uncertain constraint, probabilistic constraint, to be fulfilled should be at least 90%. So there is a constraint here, but that constraint is probabilistic. The constraint is that C up lower than or equal to F up M for every M. Remember, this is a stochastic or uncertain parameter. There is an empirical distribution for that. So we want to know that this probabilistic constraint to be fulfilled for all minutes together, the probability for that should be at least 90%. Are you following me? So C up is our reserve capacity in kilowatt. F up per minute M comes from our historical data. It's the empirical distribution. For each minute, because we have minute level data, and epsilon is 0.1 as per P90 requirement. And this constraint is a chance constraint. Good. So we just discussed that what does this probabilistic constraint, also called chance constraint, enforce? Chance constraint programming, it's a well-known class of optimization problems under uncertainty. What kind of chance constraint is it? It's a joint chance constraint because here you have multiple constraints you have one constraint per minute. So if you have 60 minutes, you have 60 constraints here. So it's a joint chance constraint. You can also have a single chance constraint that you have only one constraint. But here is a joint chance constraint. We have more than one constraint within function P. Good. Are you following me so far? Good. So here I put the minute level data because of the data availability I have. But if I had a chance to have second level data with second resolution, does it make our decision-making optimization problem more flexible, or more flexible means less conservative, or more conservative? Let me reformulate my question. Based on minute level data, let's say that I calculate my optimal C up, and imagine for a specific hour, it becomes 10 kilowatt. If I have access and if I use second level data, do you expect this value become 11 or 9? Is it clear what I'm saying? With having more resolution, more data with a higher granularity, do we expect to have a higher bit or lower bit? Who says higher bit, like 11? Or who says lower, like 9? Okay, let me repeat the question so maybe we can get more answers here. So what I'm saying is that for every hour, like hour 2 to 3 p.m., I have 60 data points for that hour, and I end up in 10 kilowatt. It means that in 10% of the minutes, like 6 minutes, I can have a failure. It means that though my bit is 10 kilowatt, but my consumption might be less than 10 kilowatt. So that's why I have overbidding. But if I had a chance to have second level data, right? So how many seconds we have per minute? 60 times 60, right? So we have 3,600 data points. If I had a chance to have second level data, so then in that chance constraint, I'm saying that in 10% of the times maximum, like 360 seconds, you can fail. You can have a flexibility a bit, which is more than your consumption. By that, are you going to have more flexibility or less flexibility? Yes? More flexibility. Why?
Because if we had 1 hour with the minutes, we could only violate 10% of 60.
Yeah.
But now we have 10% of 3,600.
Yes. For example, in this case, if in a second, in a minute, you have a failure, the whole minute is counted as a failure. While if you separate them, then maybe you say, okay, in 1 second I have failure, in other 59 seconds I'm fine. It gives you more flexibility. So if we have a second level or second resolution data, maybe instead of 10 kilowatt, we manage to bid 11 kilowatt. Right? So more data can help you to have a better business case. Are you following me? Good. But, well, unfortunately, I didn't have second level data. So how we can solve this problem? We cannot solve this problem as it is. So there are many different ways. Still, it's active research in OR community, how to solve chance constraint problems. Ideally, we can reformulate it analytically. If our distribution has good properties, and I'm not going to talk about that, you may have a chance to analytically reformulate this. But here that we are using empirical distributions, it will be very unlikely that our distribution has good properties we are looking for analytical reformulation. So what we are going to use here is sample-based solutions. So what we are going to do, to be honest, is that we are trying to reformulate this chance constraint to be a scenario-based stochastic programming. So as I said, this follows empirical distribution, right? Draw samples, and then you can reformulate this problem as a stochastic programming, like our previous lecture with scenarios. There are two models, at least in the literature, for sample-based formulation or solutions. One, it's called also X. It comes from this paper, and also X stands for the first initials of the authors, Ahmad, Luitke, Song, and Jie. Yeah. And the second way is conditional value at risk CVAR approximation. So we reformulate or we approximate chance constraint by CVAR constraint. And last lecture you learned about CVAR. Okay. First you can ask me that, okay, Jalal, how many samples I need to make sure that these samples represent well the underlying distribution? So there is a very nice paper, reference 3, that tells you how many scenarios you need at least. Okay, I'm not going to present that. I'm not going to cover it here. And in your assignment, I think I gave you a number, how many samples you need. But if you want to know a lower bound of the number of samples, you can read that paper. Okay. Also X. Let's start with that. What it does, you reformulate chance constraint to a sample-based or scenario-based MILP. MILP is mixed integer linear programming. If you think that if you realize that we have too many binaries, it's computationally hard to solve, you can have LP relaxation. But no, if you realize MILP is okay, we can computationally solve it, it's not a big problem, you can stick to there. You can just stop there. You can solve MILP reformulation. But if you see that, as I said, MILP is a very big problem to solve computationally, you can have LP relaxation and solve it iteratively. I'll explain that. Good. So this is what we saw. Chance constraint problem for optimal FCRD up problem. C up is your FCRD up bit with chance constraint. We can reformulate it based on samples. We can reformulate that problem to be like this one. And here, omega is index for scenarios or samples. So as I said, what are the samples? Samples are simply samples that you draw from this empirical distribution for every minute. Random samples. Okay? So omega are samples. So could you please check it for a minute and tell me whether you agree that that chance constraint is, or let me reword. This MILP problem is stochastic mixed integer linear program, is sample-based reformulation of the original chance constraint program. Please look at it for a minute and try to justify if they are, I'm not saying identical, it's the reformulation. And by the way, M is a big value. Think of 10,000. So here M is a big value, like 10,000. It's called big M. Is there anyone who may have the initial guess, initial idea? Anyone? Thomas?
Yeah, so we replaced the probability constraint with the binary variable, which is indexed probability better per scenario,
Which one is binary?
y.
Yes. Ym omega is a binary variable. So you have one binary variable per minute per scenario or per sample. Okay?
And then we use the begin to account for the violations regarding when y is 0 or 1.
Mm-hmm.
So when y is 0,
When y is 0,
we don't have a violation.
so when y is 0, this upper bound becomes 0. It means that c minus, so what is this?
This is the distribution of.
Is it a distribution? This was a distribution.
Scenario index.
It's the sample. It's one of the samples, the sample omega, that we draw from the distribution for minute m. So this is a distribution, but this is a sample omega from that distribution. So this is a variable, sorry, that's a single value. Like 5 kilowatt, 10 kilowatt. Okay, so when C up minus this sample, like 5 kilowatt, is less than or equal to 0, what does it mean?
We satisfy the constraint.
Yes, we satisfy the constraint, right? So it means that there is no violation. Because if this is 0, the upper bound is 0, then C up indeed less than or equal to F up M omega. Very good. Yeah.
But if y is 1, then we have that C, the begin is activated and then we violate the constraint.
If y takes optimal value of 1, then upper bound becomes big M, like 10,000. Then C up minus F is less than 10,000, right? It means that we are violating the constraint. For example, think that F is 5 while C is 6. So 6 minus 5 is 1. 1 is not less than 0. To avoid that, we put, or it might be not less than 1. So that's why we put a big value of M, to make sure that this constraint is always feasible. Right? So what you're saying, Thomas, is that, if y is equal to 0, we are not violating the constraint. If y is equal to 1, we are violating the constraint. Okay? And what's the last constraint?
For the cases that we have a violation, we constrain that it must not be higher than the number that we have from the requirement.
Exactly. This is our budget. How many times, for how many samples and minutes we can violate the constraint. So here, this left-hand side of the constraint calculates for different minutes, different scenarios, how many times we violate the constraint, and it should be lower than or equal to Q. Q is our input. It's our budget, violation budget. And what is our violation budget? Okay, we have Y per minute per scenario. And how many times we can violate? 10% of the times. So here we have 60 minutes. Let's say we have 100 scenarios. 100 scenarios times 60 minutes times 10%. So our budget is 600. Did I say correctly? So let's say we have 100 scenarios or samples. We have 60 minutes. So our budget, how many times we can violate, is 10% of 100 times 60, right? Which becomes 600. So it means that 600 of the times y can take value 1 over different minutes, over different scenarios. Is it clear? Did you get the whole point? This is exact sample-based reformulation of the original chance constraint. Okay? Very good. And you are going to implement that to your problem, exactly this problem. So let me challenge you. By decreasing Q, let's say that it's not 600, but it's 500. What will happen to C up? Will increase or will decrease?
Decrease.
Will decrease because you are reducing its budget for violation. By increasing Q, saying that not 600 but 1,000, you provide more flexibility for the optimization problem to violate this constraint. So then you are going to get a higher C. Is it clear? And always you try to maximize C because of the objective function. So as long as this budget constraint lets you, you will increase C up. Is it clear? Very good. Good. So in your task, your assignment 2, this is a mixed integer linear problem, right? Because of binary variables. How many binaries you have? 1 per minute, 1 per scenario. So for example, so in your assignment, I didn't ask you, I mean, you have only 60 minutes, and I think I asked you to produce, I don't know, 100 scenarios, 200 scenarios. So I think it's manageable to solve this MILF problem directly in your tasks. So you can stop here in your assignment. But think of a case that maybe you don't have 100 scenarios, but 1,000 scenarios. Then the number of binaries will be 60,000. You have ym omega. You have 1 binary per minute per scenario. Or maybe not, you don't have 1,000 scenarios. Maybe you have 10 million scenarios. You want to really represent well the underlying empirical distribution. Then maybe you may realize that this MILF problem is really hard to solve. If it becomes the case, then these people who wrote also X paper, they suggest you to relax Y between 0 and 1 and solve this problem as LP, linear program, iteratively. Eventually, it will provide you feasible but not necessarily optimal solution. Okay? So I think it's good for you to know that, but for your task, I don't think you need this iterative LP. You will be able to solve this MILF problem directly. Are you following me? Good. There is also a second way, still sample-based, to reformulate this problem. So here, with chance constraint, you don't mind at all how big your violation is. You only count how often, how many times violation happens. But you never bound, you never restrict the magnitude of the violation. And actually, P90 didn't ask you. But the second way to solve this chance constraint problem is that to reformulate it as a CVAR constraint. And you remember from last lecture, CVAR takes care about the magnitude of the tail of the distribution. So by using CVAR instead of chance constraint, you are becoming more conservative than what Energinet asks you. But if you want to use CVAR, I wouldn't like to, I will not go to the way the reformulation happened, but you can use this optimization problem in your assignment. It's a linear program. There is no binary. Still, the objective function is maximizing the bit. Now again, you have samples, and also you have 2 extra auxiliary variables of beta and zeta per minute per omega. And now you can solve this problem. If you want to know that how this CVAR is built, you can again check our previous lecture. But yeah, you can see it as a LP problem, and you can use this in your assignment. So that's the second alternative to reformulate this chance constraint. Okay? So what happened, just to summarize, the summary is that we end up in a chance constraint problem. Then we draw samples. We have samples. I don't know. And then we have two ways of solving. Either we go for exact MILP, right? The previous formulation. Or based on CVAR, you have LP, linear program. This is more conservative because also you care about how bad you constrain the magnitude of violation. While here, you only count and constrain the number of violations, not severity of the violations. So here you have mixed integer linear program to solve. Here you have linear program to solve. This is easier to solve. If you realize that this MILP problem is hard to solve, which I don't think it will be the case for your assignment, then you can relax binaries and solve the problem iteratively. It will be iterative LPs. And then it will be also X algorithm. So for your assignment, what you are going to do is you solve this one, you solve this one, and then you will compare the bits, the optimal bits that you got from two cases. And then you will compare them out of sample. Is it clear? Good. Now let me move on. So what I'm teaching now, from now on, it's not part of your assignment. So Energinet has extra requirements for stochastic flexibility units, flexible units like batteries, those assets with limited energy reservoirs. So on top of P90, Energinet has something called LER requirement. LER stands for limited energy reservoirs like batteries. So I will not go in deep, but just reading. So again, this text in green box is borrowed from an Energinet report. It says that if you wish to pre-qualify 1 megawatt for FCRD upward, you must reserve 0.2 megawatt in the downward direction for normal state energy management, as well as 20 minutes of full FCRD upward delivery, or 0.33 megawatt of energy. It took a lot for my students, for Emil and Gustav, to really understand what this requirement says. And, well, you can go and read the paper, the implementation. So this extra requirements shrinks the downward flexibility to this area and upward flexibility to this area. So by this extra requirement, you have less flexibility. But you can read the paper to fully understand what this LER requirement does. So eventually, we ended up in this chance constraint problem in that paper, in that master thesis, and you don't need to implement that for your assignment. So now, as you see, is that we optimize FCRD up and down both together in the objective function. And now, before you only had this constraint. But now LER requirement also added two more constraints. But what they are, I don't want to cover it here. Just I like to give you some ideas that, well, there are more requirements than just P90. Okay? For example, to give you an idea, now we have three uncertain parameters. How much flexibility up we have, how much flexibility down we have. They are stochastic parameters. And also we have this, the third one, probability distribution of downward flexibility available in minute m, such that the aggregated battery can be charged if the cell is fully activated for the next 20 minutes. Why 20 minutes? It comes in the regulation. Yeah. Good. Again, you can, Emil and Gustav, they solved this chance constraint problem using both also X and CVAR algorithms based on sample-based reformulations. And they ended up in these results. This is out of sample results. The x-axis shows the frequency of orbit and how many days the orbit is happening. For example, if we use CVAR, you see that in 150 days, the frequency of orbit is 0. No orbit happened. While that for also X is way less, because we know that also X is less conservative than CVAR. So what Emil and Gustav they did, they saw that, okay, also X exposed, the mean of violation is 10%. 10% of the times exposed, our service is not available. While in case of CVAR, because it's very conservative approach, the mean is 4%, while we had a budget to violate up to 10% of the times. Another interesting observation that in their work, it might be interesting for you. Remember, we have 1,400 EVs. They say that, okay, if we put all these EVs in one portfolio, there is only one aggregator. This is how much flexibility we can get. It's not in flexibility, also it's total revenue. But if, for example, we split our EVs among 2 portfolios, this is how much we are going to earn. Or if we split this 1,400 EVs among 20 portfolios. And as you see, in this case, you almost earn nothing. While by having more and more portfolio, you earn more. And what it shows is that there is increasing synergy. By putting more assets in your portfolio, you can earn more. Again, because of this aggregation effect. Yes, so just to wrap up, this lecture was a bit more practical, more application-oriented lecture than the previous ones. It's a real case study based on Energinet requirements. So we discussed about the Energinet requirements, both P90. So you will implement P90 requirement in your assignment, but not LER. But if you are interested, you can read the paper. And we solve it as a joint chance constraint program. We saw that also X provides a better reformulation, better performance, while CVAR is more conservative, and there is a synergy effect among assets in the portfolio. But there are many, many, many other things that you can do. For example, we used historical data directly for bidding the capacity, the flexibility for the next day. So what we missed there is forecasting. So maybe instead of doing that, what you can do is that first you use historical data to forecast how much flexibility you will have tomorrow, probabilistic forecast, and then go for bidding problem. Will it be useful or not? It's unknown to us at the moment. Maybe you can get higher resolution data, maybe per second, and then you can see how much, is there any meaningful difference or not in your business case. Here we only talked about FCRD, but you can augment it to other services as well, like FCRN, AFRR, MFRR, FFR, so you can have multi-market bidding. And I can tell you, multi-market bidding is a very complex task. And here, intentionally, we picked FCRD because it's an easier problem. because it's not energy intensive. So when it's being activated, FCRD, the EV owner will not really notify that because it will be activated for a few seconds. But if we use EV flexibility for example, AFRR or especially MFRR, then they are energy intensive services. The activation, the energy delivery upon activation is significant. So then there will be rebound. For example, if you ask EV fleet to reduce their consumption for the next 20 minutes, well, at some point, they want their battery full. So it means that at some point, they are going to start increasing their consumption, right? Then it will complicate the problem. Does location of assets matter in low inertia grids? Here we assume that it doesn't matter where EVs are, as long as they are in DK2, for example, they can provide, we can put them in a single portfolio, and that's fine. But there are some studies from our colleagues with more expertise in dynamic and stability. They say that in low inertia systems, it matters where resources are. Okay, then that's an extra constraint. More heterogeneous aggregation of stochastic assets. Why we are only talking about EVs? Why not to think of an aggregator of also different assets? Maybe we can have a portfolio of 1,000 EVs, 1,000 heat pumps, multiple wind turbines, I don't know, other flexible assets together. And maybe they can help each other. Maybe the synergy that we observe there will be even more. So that could be also an interesting way to further go beyond this study. The other one, you can also read this paper in the last item. Well, again, we derived empirical distribution from historical data, and we assume that that empirical distribution is a good representative of future distribution. But how can we know that? All the times, everything is changing. Maybe distribution tomorrow is totally different than what we observed the last month or the last 2 months. So then you can think of something called, for example, distributionally robust optimization, saying that, okay, good, I have empirical distribution from historical data, but I define a budget for my optimization problem to make that distribution even worse to me. And then I optimize my problem, right? Assuming that nature will make empirical distribution even worse to me. I found that worst distribution, and then endogenously at the same time I solve my bidding problem. So this will be useful if you don't trust enough to your empirical data, right? And if you realize that, okay, you can easily do that, see that, okay, how much historical data is useful for future. If you realize that they are not representative enough, then you have to do that. So there are many ways that you can extend this, this type of works in your future study if you are interested. Okay? That's all. Any question? Good. Then this was the end of this lecture and this course.